Okay, same again. This is December mock, our mechanics, second question on our mechanics. And this is about graphs, which is always a tricky one. So let's see if I can, draw this. Like I say, pause it, if that helps, and then we'll see where we go. So for this model of motion, blah, 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 state the value of velocity, state the time, sketch the velocity time graph. Okay. So I'm going to, whoops, that wasn't very good. Okay. Right, velocity will go up here, and this will be time. Okay. So in the model of motion, it starts from rest, and so it starts from rest means its t is 0, and it's going to move with an acceleration 0.3 for 80 seconds. It has to be a diagonal because it's accelerating, and it's a constant acceleration. So we'll be at 80 seconds at this point. So if we have acceleration, which is our gradient in this case, so acceleration equals rise over run. So we've said acceleration. So the acceleration equals rise over run, which in this case is velocity over time, which kind of makes sense. So 0.3 equals velocity that we don't know over 80 seconds. So 0.3 times 80 means that velocity must be 24 meters per second. So this point here is 24. So that's a good start, meters per second. Okay, state the time for which the train is decelerating. So after this, then the train moves at constant velocity. So that's constant velocity before decelerating. Decelerating with a constant 0.5 coming to rest. So then same kind of thing applies, but decelerating is obviously minus a half really. We know that the velocity is 24. We don't know the time, which is time. So time equals 24 divided by 0.5, so that is 48. So this bit here is 48 seconds. Okay. Oh. And then from all of that, obviously, we've got the graph that we now have here. But I'm just going to put in, we don't know what this bit is here, so I'm going to give that the capital T. Okay. Total time. So given we got a velocity time graph, the area underneath the velocity of the graph is the displacement, and they've told us the displacement is 4800 meters. So we need to work out the area under the graph. So area under graph, also known as 4800 meters, will equal the area of the first triangle. I'm going to do it into three separate things. So we've got half base, which is 80 times height, which is 24, plus I'm going to do 24 capital T plus a half times 48 times 24. That equals 4800. So 0.5 times 80 times 24 is, so that's 960 plus 24T plus 576 equals 4800. So 24T must equal 4800 minus 960 minus 576. Oh, that's a horrible number. 23264. So that equals that divided by 24, which gives us 136, which is a really nice number. So, but we want the total time, so we've got to add all that on. So we've got total time would be 80 plus 48 plus 136 plus 80 plus 48 gives me 264 seconds. Oh, 264. I think I'll write that again. 264 seconds is the answer to that one. Suggest one improvement. Classic, really. Our models are always rubbish because we say it's got constant acceleration in these ones, and if you're on a train, there's no way it speeds up, stays that, and slows down, because there's always something on the track, or there's some problem, or you're going around a corner, for example. So it's always along a straight road. So variable acceleration would be an excellent answer for that.